In the world of modern electronics, the OLED display is a marvel of physics and chemistry. Unlike traditional LCDs that require a bulky backlight, OLED, or Organic Light Emitting Diode, technology allows every single pixel to act as its own light source. This means when a pixel is off, it is truly black, providing an infinite contrast ratio that was once thought impossible. The engineering challenge is immense. We are talking about stacking layers of organic carbon-based films that are each over 1,000 times thinner than a human hair. To build one, engineers must orchestrate a dance of atoms in a vacuum more perfect than outer space. If even a single microscopic speck of dust or a molecule of water vapor enters the assembly, the entire panel is ruined. This is the story of how we turn raw glass and rare earth chemistry into the window to our digital world. It is a process defined by nanometer precision and brutal environmental control, where light is not just filtered, but born from the very molecules of the screen itself. We are moving beyond the era of the liquid crystal and into the age of the self-emissive diode. Every OLED display starts with a foundation of extreme purity, the substrate, usually made of a specialized borosilicate glass or high-tech polyamide for flexible screens. This mother glass must be perfectly flat. Any deviation larger than a few nanometers would cause the intricate electrical circuits to fail during the lithography process. The glass arrives in sheets large enough to cover several dining tables, yet it is often less than 0.5 millimeters thick. Before a single transistor is laid down, the glass undergoes a violent cleaning ritual. It is blasted with deionized water, scrubbed with ultrasonic waves, and treated with ultraviolet ozone to strip away every last organic contaminant. At this stage, the factory environment is a Class 10 cleanroom. This means there are fewer than 10 particles of dust per cubic foot of air. For comparison, the air you are breathing right now contains millions of particles. This level of sterility is non-negotiable, because at the scale we are building, a single skin cell is like a mountain blocking a highway. Once the substrate is chemically pristine, it is ready to become the nervous system of the display. To control millions of individual pixels, we need a massive network of switches. This is the backplane, a complex grid of thin-film transistors, or TFTs. In high-end OLEDs, we use low-temperature polycrystalline silicon, or LTPO technology. The process begins with sputtering, where a plasma of argon ions knocks silicon atoms off a target and deposits them onto the glass in a uniform mist. But this silicon is amorphous, meaning its atoms are jumbled. To fix this, a massive excimer laser sweeps across the surface. The laser pulse lasts only nanoseconds, heating the silicon to over 1,000 degrees Celsius for a fraction of a second. This causes the atoms to rearrange into a crystalline structure, allowing electrons to flow much faster. Next comes photolithography. A light-sensitive polymer is coated on the glass, and a high-precision mask blocks UV light to print the circuit pattern. Acid then etches away the unprotected areas, leaving behind a web of microscopic gold and chromium wires. This is the nervous system that will tell each pixel exactly when to fire and how bright to glow. The most critical stage is the thermal evaporation process. This takes place inside a massive stainless steel vacuum chamber where the pressure is dropped to 1/billionth of an atmosphere. Inside, the organic materials, the secret chemical recipes for red, green, and blue light, are held in crucibles. As these crucibles heat up, the organic powders don't melt, they sublimate, turning directly into a gas. This vaporized cloud of molecules rises toward the glass substrate hanging above. To ensure the colors land in the right spots, a fine metal mask, or FMM, is placed against the glass. This mask is a feat of engineering itself, a thin sheet of invar with millions of holes, each corresponding to a subpixel. The holes are so small they are invisible to the naked eye. As the organic vapor passes through these holes, it condenses back into a solid on the glass, layer by layer, atom by atom. We repeat this for each color, building a microscopic stack of hole injection layers, emissive layers, and electron transport layers, creating a stack of chemistry that is ready to glow. The fine metal mask is often called the bottleneck of OLED production because its precision requirements are staggering. Made of a nickel-iron alloy called invar, it is chosen because it barely expands or contracts when temperatures change. This is vital because if the mask shifts by even 2 microns, about 1/50th the thickness of a hair, the red subpixel might bleed into the green one, ruining the color accuracy. To manufacture the mask, lasers or chemical etching create millions of tapered holes. In a 4K display, we are talking about over 24 million subpixels, each requiring a perfectly aligned hole. Gravity itself is an enemy here. A large mask can sag under its own weight, so it is stretched under immense tension and welded to a heavy metal frame. When you look at your smartphone, you are seeing the result of this microscopic stenciling, a process so precise that it pushes the very limits of what mechanical engineering can achieve. Without the InVar mask, the vibrant, sharp images we take for granted would be nothing more than a blurry mess of light. Organic light-emitting materials have one fatal weakness. They are incredibly sensitive to oxygen and moisture. If a single drop of water were to touch the internal layers, the organic molecules would oxidize and go dark immediately, creating dead pixels that spread like a rot. To prevent this, we use thin film encapsulation, or TFE. This is a multi-layer fortress built directly over the organic stack. It alternates between inorganic layers, like silicon nitride, and organic monomer layers. The inorganic layers provide a hard barrier against air and water, while the organic layers act as a buffer, filling in any microscopic cracks and providing flexibility. Think of it like a nanoscale sandwich of glass and plastic. This entire barrier is often less than 10 microns thick, yet it must be effective enough to keep the display working for 10 years or more. Engineers measure the failure rate of this barrier in water vapor transmission rate. It is designed to be so airtight that it would take over 1,000 years for a single drop of water to seep through. This is the only way to ensure the delicate chemistry inside stays alive. Now that the light-emitting core is protected, we must add the layers that make it a usable device. First is the circular polarizer. Because the internal metal circuits are shiny, they would reflect sunlight like a mirror, making the screen impossible to see outdoors. The polarizer is a specialized film that traps incoming light, prevents it from bouncing back, but allows the light generated by the OLEDs to pass through. This is why OLEDs look so deep and black even in a bright room. Next, the touch sensor layer is integrated. In modern displays, we etch a grid of transparent indium tin oxide electrodes directly onto the encapsulation layer. This is called on-cell touch. It allows the screen to be thinner and more responsive than ever before. Finally, the driver IC, the brain of the display, is bonded to the edge using anisotropic conductive film, a glue filled with microscopic gold-coated spheres that conduct electricity in only one direction. This tiny chip translates digital data into the millions of voltage signals that bring the screen to life. Every step here is a balance of optical clarity and electrical conductivity. Before a display can leave the factory, it must survive the gauntlet. High-tech sensors scan every square millimeter for defects. An automated optical inspection system looks for mora, subtle clouds of uneven brightness, and dead pixels. Any panel that doesn't meet the strict uniformity standards is discarded. This is why high-end OLEDs are more expensive. The yield, or percentage of perfect screens, is lower than with LCDs. Next, the panels undergo aging or burn-in prevention tests. They are run at maximum brightness in high-temperature chambers of 85 degrees Celsius for hundreds of hours to ensure the organic materials won't degrade prematurely. Engineers also use high-speed cameras to check for flicker and measure the response time, the time it takes for a pixel to change color. While an LCD might take several milliseconds, an OLED responds in 0.1 milliseconds. That is 1/10,000th of a second. This final quality control phase is the thin line between a premium product and a failure, ensuring that when you turn on your screen for the first time, every one of those millions of pixels is firing in perfect harmony. The true magic of OLED engineering lies in its versatility. Because the light source isn't fixed to a rigid backlight, the entire display can be made onto a plastic substrate instead of glass. This is the secret behind foldable phones and rollable TVs. By using a transparent polyimide film, engineers can create a screen that is as thin as a piece of paper and can be bent hundreds of thousands of times without cracking the internal circuits. To achieve this, the metal wiring in the backplane is designed in a zigzag serpentine pattern, allowing the metal to stretch and compress like a spring rather than snapping. We are now entering an era where displays are no longer just flat windows, but skins that can wrap around any surface. From curved automotive consoles to wearable health monitors that contour to your skin, the precision of OLED manufacturing is reshaping our world. We have moved from the heavy vacuum tubes of the past to a technology where light is as light and flexible as the molecules it is made of. The precision is microscopic, but the impact is global. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this Tech Archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.